like this.
So, and what would happen to future space travel? Would they would track it and then avoid it, or it would?
Exactly. So that's one of the biggest issue that we have nowadays. And even frequently they have to avoid them because there are some of them up there.
Didn't the Chinese just blow up a satellite like last year or something?
No, 2007.
2007?
They blew, one. Yes. So we'll have a look. That's why, what you've seen in terms of these type of accidents, it existed. Okay, it happened once. But there were never, ever casualties for anyone in space. You know, but this can happen. So other suggestions about things that you believe are not true in what you've seen? Any comment? Yeah, please use the microphone if you want.
The only thing that I'm wondering about, why did Matt released her? Why did he let her go? Yeah, why did he sacrifice himself? There was like a
Very good point.
Yeah.
And we'll see that.
Was that like scientifically necessary? Like
Yes, okay. So I'll be there. No, you are totally right. And we'll see what's the problem in that very specific scene, but there are many ones that are exactly based on the same principle. And you will see it's something weird. You know, that's why I'm really, but very good, very, very good point. Any other comments? Yes?
Thank you. So I'm a scientist and I'm working in a lab, and we are surrounded by safety precautions, like a lot of safety rules. And at the very beginning, we see George Clooney, he's just on his thing and he's wandering around.
Yes.
And I find it like totally out of place. Like, I mean, that's the last place you would just untie yourself just for fun.
Exactly.
I know maybe you can reach a certain level of like confidence or something, but I guess people selected to go there. So they are also good at following rules.
You're totally right. There are two things in what you've just said. First, you don't go for fun, you know, in those things, because every minute costs millions, you know, so you have to be careful. The second thing is, because for safety issues, difficulties, and also it's very time-consuming to go outside, what I can tell you is that they do that 10 times on Earth in a swimming pool before going to space. So it's exactly like music. You know, you cannot just change, and you cannot just say, I'll go that way or that way. No, you've got something like, let's say, 30 minutes outside, and therefore, you know exactly every minute what you are doing. You are doing this, you are doing that, you know. And it's not mission abort or things like that, as we see. It's just, it's very well prepared. And so you're totally right also on that point. Final point, yes. And after we move on, but yes, please.
I have a question about the comment you made before the film screening. It would take more time for them to adjust back normally. Of course, for the duration of the film, they made it shorter.
You mean at the very end or during at any time?
No, in general, you said when they take off the suits,
Yep.
they need time, like 2 to 3 hours.
Yep.
And during that time, what would they be doing, like, to adjust back to normal?
Yes, two things. Okay, for the sake of the movie, it goes very fast. Okay, and they shortcut permanently, you know. And in fact, to even put the suit on, it takes close to 2 hours. Because he's not just entering in and out as you would do for diving, you know, where you just put it on. The second thing and is also to adapt the body, and it takes time, you know, so it's not as fast and as we can see it, and even worse at the very end, you know, for the body to adapt when she walks at the very end, you know, you cannot even walk. She would be in the water and she could stay 1 or 2 hours, you know, because the difference is such. Okay, so maybe let's move on. Yes, so that's the international space station, and what, you know, exactly your scene, and I think not only this scene, but many times you've got this rope or tether that is even attached to some of the spacecrafts many times. You know, you see that, and you see this reaction. And now we'll see the problem of that. Okay, but that's one of the biggest, you know, problem in the movie, I would say. So first of all, so from a scientific point of view also, because we have the feeling that all the things we see are zero gravity. Okay, totally wrong. It's not zero gravity. When you go up there, in fact, at all the altitudes that you see, you still have close to 90% of the gravity you have here. Okay, 90%. So it's almost the same. The big difference, when you look at it here, is that you have, let me put it that way and you will see. So what you have is the gravity. Even when you are here, you still have 90% of the gravity as we have here, okay? The difference is that you've got speed. Okay, but if you just go speed and gravity, in fact, you fall back, okay? So you fall back on Earth, normally. If your speed is fast enough, in fact, you are falling onto the Earth, but because of your speed, in fact, you miss the Earth, okay? So it's exactly as if you were in a lift. So imagine we are all, so this is a big lift, and we are falling all together, okay? So when you are falling, you are still under gravity, because you are falling, okay? But from the moment we are all falling together, in fact, we don't feel the gravity anymore. And therefore, we would be just in space all together, okay? And so what the satellite is doing, it's falling, okay, permanently, and missing the Earth because of its speed. And so the very important thing to keep in mind, and that's why we call that microgravity. It's not zero gravity. But the feeling is exactly so. Imagine you are in a lift, an infinite lift, you are falling, okay? And all the objects around you are falling at the same speed as you. And that's why they would stay. So I would put that here, you know, in this lift that is falling, free fall, then it stays there. And so you have the feeling that there is zero gravity. But in fact, no. You know, it's still falling with you. So the only difference when you are in a satellite is in fact that you are permanently falling. And you are just making a circle. But remember, you are still under gravity, okay? But you have this microgravity, and that's exactly, you have this feeling that you don't have a mass anymore. So that's one point. The second thing that you have seen, so is that if you have heard, they were talking about the beginning of the movie, they were repairing the Hubble Space Telescope. You remember? Okay. The Hubble Space Telescope is in fact, you know, running at exactly 28 degrees. You've got here. The space station that they go to is in fact at 51 degrees. Why 51? Is they want to have the space station that goes above USA as much as possible, okay? But what you can see, even if you wanted to go from the shuttle to the ISS, in fact, they meet only once every a month, maybe, okay? So they are not on the same orbit, first of all. So in fact, you cannot go from, let's say, the space shuttle to the ISS. Impossible, okay? Because I mean, they don't have the same orbit. And even at the end, it goes to the Chinese Shenzhou spacecraft that has a different angle. So even in fact, you know, and why they do that is precisely to avoid encounter. So they want to make sure they don't, you know, encounter, so they have different angles. So first of all, you cannot just go from one spacecraft to another spacecraft in space, because they are rotating at different angles, okay? The second thing I'd like to show you now, and that's the only equation you will see ever in this presentation, is what is called the orbital velocity. Okay, so if you have a mass in the center, that's the Earth, and you've got the satellite, or yourself, okay? When you are rotating, okay, in fact, you can compute the velocity. And the one thing you have to look at, the velocity doesn't depend on your mass at all. So if you are 1 kilogram, 100 kilograms, or 1 ton, okay? It's independent. The velocity that you have just depends, the only thing that is changing is the distance to the object. So it's the altitude to the Earth that will determine your speed. Okay, not your mass. So if you are big, small, no differences. So what you have to keep in mind now also is that the further you are, so if you go far away from the Earth, in fact, you know, this distance increases, so it means the velocity is smaller. So if you are orbiting around the Earth, okay, if you are close to the Earth, in fact, you go fast. If you are further away, you go more slowly. So let me show you now, so keep that in mind. The real equation in real things, you know, in real terms. So what you have first here is the altitude, okay? And here you've got the speed. So what you can see if you follow that line, so that's the speed of satellites. You can see that if you are here, okay, lower orbit means faster speed. So all the satellites that are low, okay, they go very fast. Now, if you go upper and upper, in fact, the speed is smaller and smaller. So higher orbit, lower speed. Okay, so very important. If you go fast, in fact, it means you are close to the Earth. If you are up there, in fact, you go slowly. So first of all, when you see that, okay, you've got the ISS at that here. You've got the Hubble Space Telescope here. And if you could hear what happened, they are telling you in the story that in fact some Chinese and Russians, you know, have destroyed communication satellites. And it is the debris of this communication satellite that is destroying the ISS and everything. Where are the communication satellites? Up there. And we are talking about 36,000 kilometers. Okay? This is about 200 to 400. So those satellites, if they were destroyed, okay, they are 36,000 kilometers away. 40,000 kilometers is the surface of the Earth. So it tells you that it's so far away you cannot even. So it's impossible, you know, that they meet, in fact. So even if those you destroyed them, they would not go there, you know. So what is very important to keep in mind is different speeds means different orbits and altitudes. So information number one, in fact, those, you know, cannot meet. And just to show you now the numbers, and that's what you will look at. For example, the ISS is almost at 400 kilometers altitude. The Hubble Space Telescope is 600. So even the difference in altitude is 200 kilometers. So imagine, you cannot go from one to the other as easily as in the movie. But even worse, you know, if you want to go those satellites that they say are exploding, you know, they are extremely far away. The second point is also, even this little difference in distance, okay, you have the feeling that it's a small difference in speed. Because I was telling you, you know, as when you go high, in fact, your speed is lower, okay? And that's what you can see here. But this looks like a small difference. But the speed difference that is 120 meters per second is in fact 400 kilometers an hour. So even if you can reach, imagine you are at the Hubble Space Telescope, you go down, the difference in speed, you know, of the spacecraft is 400 kilometers per hour larger. So imagine you would see it passing by at 400 kilometers an hour if you can reach the thing. So in fact, you cannot catch it. Just forget, you know, as we see. The other thing that was very accurate in the movie, if you could see, she was setting at 1 hour 30 minutes, and that's really the time it takes, you know, for satellites to go around the Earth at that altitude. Just one thing to show you. So this is the time it takes. You see here the period for the satellites to make one rotation around the Earth, okay? The one thing I would like to put your attention to is this, what we call geostationary satellites. The interesting thing is you can see it, because here it's 97 minutes, you can see it increases to 1 day and many days. Like the moon, you know, it's 27 days. But the 1 day is very interesting, because when you are at this altitude, your speed, you know, this is 3 kilometers an hour approximately. In fact, you will turn around the Earth in 1 day. So what it means, you are rotating exactly at the speed of the Earth, okay? So whatever object you put at this distance here, in fact, will always stay above the same point below you. So that's why we call that geostationary. So it means it's exactly there. So even if you go there, you put, you know, a ball, you put anything, it will stay just above us, for example. So if you put any object 36,000 kilometers above, it will stay forever, for 1 million years. Okay, just there. And that's where we put all the communication, telecommunication satellites. You just put them there and they stay. So very easy. Okay. So that was just one point about that. So just to summarize, what you've seen before is that in fact they have the satellites and spacecrafts, they have different speeds based on the altitudes, and they have very different altitudes. Okay. So that's why, in fact, it's very difficult to allow them to encounter each other. Okay? And now I'd like to give you the microphone.
Okay. So I'm going to talk about the symbolism in the film. And within the symbolism of the film, one of the main themes is the notion of home. And I want to talk a bit about something called the overview effect. It's one of my favorite subjects to talk about, really. So the overview effect is this cognitive shift that happens to astronauts when they see the Earth from an observer's perspective. And specifically in this film, it is the most film in the genre that gives a very close simulation of this effect to the audience or to the spectators. You know, you're up there in a spacecraft, and suddenly you're in an observer's perspective, and you're looking at Earth from the pale blue dot perspective, as Carl Sagan said. Suddenly, everything you've ever known is just floating there in an endless night on this very small marble. And when you go through that shift, as Frank White said, who is a space philosopher, who wrote a book called The Overview Effect, and I would recommend everybody to have that if you're interested in your library. And he interviewed many astronauts who went to space. He also interviewed our very own Prince Sultan bin Salman in his book, The Overview Effect. And I want to quote what Frank White, how he, it's right there. So he said that it's a state of awe with self-transcendent qualities precipitated by a particularly striking visual stimulus. This is what he describes the overview effect as. So the most common aspects of this experience are appreciation, a very deep perception of beauty, an unexpected and even overwhelming sense of emotion that happens, and an increased sense of connection to other people and to planet Earth as a whole, because suddenly you don't see borders anymore. You see the Earth as a planet, and you see humans as fellow species and not as different individuals. So there's this sense of unity that happens as well. So it's a very transformative experience, and it inevitably, I believe, makes them better human beings as well. One more thing about the overview effect is that it actually happened on, if we can go to the slide just before this one, when we have the picture. So this is the first time we as humans were able to see home from an observer's perspective aboard Apollo 8 in lunar orbit in 1968. And this picture is called the Earthrise photo. And this was the first time we were all able to see home from this angle. And there was a transformation that happened internationally after this photo was released.
And if I may
of
comment
course.
on this, that is very
Yes,
important
of
for
course.
this picture, because this picture looks normal, I mean, for us now. There were, at that time, already, satellites and probes that were taking pictures. But this one is the first picture of the Earth taken by a man, okay? And on that picture, you got the entire humanity photographed by one man. It's the first time ever. When you think about it, it's really strange and funny. So please, go on.
Yes, and also what I love about the overview effect is that it just goes to show us that in a very non-human environment, there is a very human experience happening, meaning it's almost sacred and it's almost mystical what they go through. And you can also use the term enchantment when you talk about the overview effect. Yes, this is clearly defined by a space philosopher who interviewed all these astronauts. And it's very important, as I said, to talk about this because in the film Gravity, going back to Gravity, as you saw, the whole film, most of it, or let's say 90% of it, was in Earth orbit, more than any other space film or film in the genre.
Yep, perfect. Let me then move.
Yes.
Now, go back to physics. What you have, as I was telling you, different speeds means different orbits and altitude, okay? Now, if you remember, those are the two moments, we were discussing before, okay? Now, I'd like to make a quick experiment, and I need a George Clooney, and I need a Sandra Bullock. So who would like to be one of them? Sandra Bullock, please. And I need a George Clooney. I don't know. Any George Clooney interested? Please, please. Good, good. And so now, let's go back to this scene, okay? Now remember, if you are on the same altitude, okay, normally you have the same speed. Am I correct? Yes. So now you are here. If you can take this, you can take that. So now imagine you are exactly as they say, like this. Now you are exactly, in that scene, not moving, okay, at the same altitude. So what it means, you both have the same speed. Okay. Now, if you put it down, what will happen? Exactly. So you leave it that, you stay where you are. And so in no way, you have those two scenes where the people just say, and then, no way. So it's totally wrong. This cannot happen. Who's pushing him? He's just doing this, and then, so magically, from a physical point of view, someone is pushing him. And even worse at the top, she just unbuckled, a belt, and then, as if someone had kicked, her, boom. So this is totally wrong. Now, if we go back here, okay. Now, what I was telling you, this is an orbit, an altitude, okay? Now, imagine you want to meet her, okay? You may think, let's pull it. Okay, if you pull it, what will happen? You start accelerating, yes? Yeah, you start accelerating. So let's say you pull, okay? Then you accelerate. If you accelerate, you change altitude. And therefore, and what happens? No. First, the first thing is, from the moment you get speed, so you try to get to her. In fact, as you remember, if you go faster, you go lower. And so if this is, let's say, or if this is the Earth that is there, so you start moving that way, and in fact, you will go there. And so slowly, if you do it, in fact, you will totally miss her. And the more you accelerate, the more you go away. Yes. So there is no way you can get to her by pulling. No, same, you gain speed. Even if
she's holding on?
No. Because whenever you do that, you accelerate.
What if we did the same time, one by one?
No, because she will accelerate in that way, so it doesn't work. So how would you do that? You want to meet. Even at some point, when they want to have those two satellites, you want to encounter another satellite. So very simple, you will see. Now that you are here, just forget about the rope, okay? Now, you know that she's, at the moment, we are both rotating that direction, okay? Simply what you do, one step, away from the Earth, so maybe move that way. Now you are going slower. So you are exactly getting there. So you just go there, and now stop, and here you accelerate. So you just at the last minute go a bit faster, and then you are together. You got it. So in fact, very counterintuitive, but very simple. So in fact, we want to get together. What I just have to do is to escape, from the Earth. And in fact, I go slower, and you go past by me, and then I go back to you. So in fact, what you see, first of all, this is totally wrong because, there is no new forces. But in fact, there are ways to even get to the point you want by simply playing with those games. I accelerate, decelerate, so getting faster or, away. So you got it? Everybody got it? So good. Thank you very much. Sandra and George. Good. So if we go back, to this, that's exactly what I was telling you at the top, is that in fact, objects that are in the same orbit, they move at the same speed, so you cannot have one astronaut tow another continuously. So whenever you pull, in fact, the person will go away. So never, if you are in space one day, okay, don't pull on anyone because you will lose that person. The second thing, and that's what I was telling you, is that there are ways, very simple ways, to make an encounter, But if you take the way, so that's what I've just explained to you, but the way that is shown in the movie, if you want to go straight, as I said, you are accelerating, and therefore you are moving away, and therefore you have to compensate again. And so the way they were doing, of course, you have to permanently, as I was telling you, you just, get a bit away from the Earth, you let whoever you want to meet, the satellite or someone, and then you go back. Very simple. Sorry? So exactly, if you go back, to that part, you could compute it if you really want to do it. You can see that, it's a lot of kilometers, okay? But very quickly, in fact, you gain speed. So the difference is very quick. So let's say in maybe less than 10 minutes, okay, you would do 50 kilometers, easily. If you want to get closer, so at some point they say, oh, this satellite is at 100 kilometers from us, And in fact, in less than half an hour, without using any, trick as she did, in fact, you can do it. So it's much less, once you understand, it's much less complex to be in space, from that perspective. Huh? Good. So now you understand that this is not realistic, but that life could be easier for them, you know, if they could choose the physics, you know, correctly. Now, your turn.
My turn. Going back to symbolism in the film, which we're also going back to the role of emotions and feelings and how when evoked can make such a grand subject such as space and the cosmos come down to a more human level. And in a way, you know, Gravity didn't get obviously everything right, but it also helped us or made us interested in subjects we could groan about a bit in high school physics classes, right? Right? Am I right? And I just want to just talk about the duration of the film quickly before I go into these symbols. So it's considered short when you're looking at space operas or films within the genre. 90 minutes is considered very short. Why? Because it's one major event from start to finish. This is really what makes Gravity also very distinct in terms of film in this genre. And the themes, most of them are very existential. If we're going to look at loss and escapism and the idea of acceptance, you see loss in two very apparent parts. First, the loss of Matt, who is her colleague, and the rest of her colleagues. And through that loss, she is also going through the stages of the loss of her daughter. So at the end of the day, this is a story of a grieving mother. This is really the core of the film Gravity. And the idea of escapism is really interesting because it's such a big metaphor as well. She is losing herself in work, and this is the ultimate escape. She escaped above the atmosphere. It's also a huge metaphor for the concept of escapism when going through such dark times and dark emotions. There's a quote that made this also very apparent in the film. When Matt told her, listen, do you want to go back or do you want to stay here? I get it. It's nice up here. You can just shut down all the systems, turn out all the lights, and just close your eyes and tune out everyone. There's nobody up here that can hurt you. It's safe. So this is a very clear quote that reflects on the concept of escapism when going through the stages of grief. And then also another quote is when Matt told her, what do you like about being up here? And she said, the silence. So this is also a very big quote when it comes to this concept of escapism. And when we go into the idea of acceptance as a part of grief also, as we said, this is a story of a grieving mother. This is really the core of the film. And how she's learning to let go through this ultimate journey. We realize there's one very clear moment of acceptance where she accepted what she went through. And this is when she talks to Matt, or the figment of Matt, about her daughter. And she asks him to tell her daughter that she found the red shoe. In this scene, we realize she has gone through that stage of acceptance, and it's very clear. This is again talking about emotion and how adding that to science fiction or these films that deal with such immense subjects, we can all relate to, even if she's an astronaut, upon the ISS. We all relate to these feelings somehow as humans.
Good. So now I'd like just to move on to 2 or 3 minor points, but that are also counterintuitive. What are the dangers, in space? Because what you've seen was kind of a fantasy of what we believe would be the most dangerous thing in space. And in fact, those are all the problems you have. And I would say, if you look at what you have here, the only problem that is really related to the movie is this old-style environment. So it means you may have major problems, let's say. But in fact, and really the order is not done by mistake, the biggest danger when you go in space is radiations. Because as we stand here, in fact, we are protected. We have a big shield that is protecting us. And you cannot stay, and that's why they are, when I showed you, the space station is at 400 kilometers, from here. Why such a low, orbit? We could be 1,000, we could be 2,000. It's not really difficult. The real difference is that when you are at 400 kilometers only, you are still protected. And even then, they stay, let's say, 3 months, 6 months. Some of the largest time is almost to a year, but they don't stay longer. And the main reason is that. And if you've heard about traveling to Mars, things like that, the biggest danger to get to Mars is in fact, you will die from a cancer before arriving, maybe, So the second is, and we'll look at that a bit more in the next slide, is what is the effect of the microgravity, because it changing your body. So of course, you've got a difficult environment, and those two also are very difficult. I mean, we were talking about isolation and confinement. This is something that is also very difficult. It seems easy, but in fact, imagine you have to live in a small box with typically 5, 6, 7 people, but permanently. So it means you eat, you sleep, you do everything for a few months with the same people. And I can tell you very quickly, people, have animosity for a minor point. And that's something that is very, very difficult to manage, in fact. Team dynamics, even sleep disorder. If you cannot sleep, what do? Do you take medicine? But then, that's problematic. And also, the other thing, if you think about even, if you need, let's say, you break your arm, or you need to do surgery, who can do it when you are in space? So maybe you want to be trained, or whatever. But it's very, those are really complex things. Another thing that you've seen in the movie, those fires. The one thing you have to know about fire is just if you look at that. As you know, when you start, a flame, you've got hot air. And as you know, hot air is lighter, in terms of gravity, than cool air, okay? So naturally what you have, hot air will follow the flame, that's called convection, going up, and cool air will go there. Now, if you don't have gravity, once you start having hot air, where is it going? It's staying where it is, okay? So in fact, the flame and the hot air is staying there. The problem is if you don't bring new air, so it means oxygen, you won't have a flame anymore. So in fact, in the space station, you don't have fires. Okay, so forget about the big flames you've seen in all directions. That doesn't exist. However, you've got fires without flame, but with smoke. And that's the real thing that happens. And whenever there is a real fire, because it happens, okay, the first thing you do, you put a mask, a gas mask, because you want to prevent. Then you stop the fire, but you won't have flames. In fact, it's just, you will smell it, maybe, okay? And so what you've seen with those big flames going in all directions, that's totally, impossible. Now, another thing that is also problematic is all the space flight, changes. There are many things that are visible effects, so you can see a lot of them, that are directly, but you also have hidden effects, like loss of calcium, dehydration, radiations, and even loss of muscles. And most of the astronauts, they have to train 6 hours a day because, we permanently walk, we permanently do activities. So when you are in space, in fact, you have to train extra because you do no exercises. And that's really dangerous. Because if you don't exercise, your heart, diminishes the pressure in the blood, and also your body, so muscles will diminish. So exactly as if when you are in a bed permanently, in fact, your muscles, are diminishing. And you have even more problems when you want to do sport again, so when you go back on Earth. And that's a big issue. And just to show you one thing that happens directly, here it's what you have, so it's the arterial blood pressure, in your body. That's on Earth, okay? So that's 1G means gravity, the normal gravity here, okay? So what you have in terms of pressure, you've got heavy pressure here because the blood is going, through your feet, okay? At the heart level, it's about 100, and in your head, it's about 70. So you have less pressure, in your blood, at the head compared to your feet. Now, what happens with your heart? Your heart is precisely pushing your blood to your head because there is not enough blood, permanently. Now, when you are in microgravity, your heart continues to pump the blood to the top, So what happens? All of a sudden, okay, you got a lot of blood in your head. It's exactly, if you walk on your hands, okay, all the blood is going down, but imagine that this is permanent. So you've got permanent blood to your head. And when you go back, if ever you go back, if you've seen when she was in the water in the end, in fact, you have much less pressure because the heart is now used to pump much less, and therefore you still have blood, in your feet, but much less pressure. So if you compare, you've got half the pressure. And if you watch, when astronauts are coming back, they are put in a chair and they don't move for a few hours, and they cannot walk. You search if you want on YouTube, you will see the guys when they arrive. People are taking them, and putting in a chair, and they don't move because they cannot. Otherwise, they faint, directly. And just to show you the effect on your head, if you go, you can see the head difference, between this and that. So that's really when the blood is going to your head. So imagine if tomorrow, if you go in space, okay, you will be nicer, I guess. The other thing that is difficult, as I was saying, you are eating all together every day, and you are sleeping also all together. And so you just stuck to the walls, okay, to sleep. But what you can see is that you live close by, permanently with people. And that's where it brings this problem of human relationship in a non-human environment. So please.
I guess people are going to be less excited about going to space after this presentation. I mean, this is just a very clear observation that how precious, right, planet Earth is. And as we said, human relationships in a non-human environment. Going back to the film Gravity, there is the relationships she had with her colleagues, and then Ryan's relationship with her daughter as well as a mother. The importance of human connections and human relationships, because at the end of the day, and one of the main symbols and themes that the director specifically wanted to talk about or portray in the film is that machines at the end of the day can't save us. Without human connections and without that human interaction that is beyond explanation, sometimes it's beyond logic, it's a chemistry that takes us almost from the physical to what we would call the meta even. And these feelings that were evoked throughout the film by simply looking at the Ganges from Earth orbit, or a visit from a figment of her imagination to give her that drive and that impetus to go home, or her love for her daughter. So this is a signal of a dimension of reality that lies beyond technology. And this is something that really was clearly portrayed within the film.
Thank you. So also when you had just 1 minute on the oxygen that you've seen, there was, when she was out, maybe after what I would consider 30 minutes, she was running out of oxygen, you know. And all people going outside, in fact, they have 8 hours of oxygen plus 30-minute reserve. And so typically you go out for 1 or 2 hours, but you have reserve for 8. So it means normally you don't run out of oxygen when you are doing a mission like that. The second thing that is very important is the main problem you may encounter if you're outside is precisely if you have a puncture from a small object, directly. But normally they are over pressurized, and therefore you can, stay even with a puncture or even several for 30 minutes. Because if you use all the 8 hours of oxygen, that's enough for 30 minutes if you have, a real failure in your suit. The second thing that you have also in the end is when she's running out of oxygen, typically, in fact, you are not necessarily sleepy, but in fact, you are typically laughing. So you get more dizzy and happy, more than depressed as she is and sleepy. That's not true. It's exactly when you go in the mountain, when you are depleted, it's different. And also, I would say it's a cheerful death because you are happy until you stop, So it's not at all what you see. Next one, exactly we were talking about when you need to bath or to go to the toilets, the big thing is that you cannot use a lot of water. And so typically, especially, to wash their hair, they use water directly on the scalp, okay? But also, it's dry shampoo, dry soap, so they use minimum water, when you are in space. Next one, when we saw her getting out, okay, this is the typical suit that you would have, not just, the underwear, as we could see. The second thing that is very important, contrary to what you see in the movie, in fact, this is to fight against heat. Because the thing you have there, when you have no oxygen, no air, is in fact you can boil. So, for example, if you remove your helmet, okay, contrary to what we think, we believe you will be frozen in a few seconds. That's totally wrong because there is no air. And the cold is coming from the air. And the problem is the opposite, is your skin, in fact, will get a deep pressurization, and in fact, it will increase the temperature of your body. And so typically when you don't have air around you, you would boil quickly. And what you have here is in fact a freezer. So when you are in space, you are fighting against the heat and not against the cold. And that's counterintuitive again. And now to move to you, to that scene when she gets out,
Yes, this pivotal scene.
Yes.
This pivotal scene of the film, which takes me to the most important symbol or theme in the film, Gravity, which is death and rebirth. So she was in a state of metamorphosis, you could say, throughout the film. And in this scene particularly, you could see that there's a symbolism of a fetal position inside the womb. And this is the first, let's say, the first encounter we have with this idea of rebirth. And then we also have a beautiful symbolism of primal longing or just being primal animals when she starts, when you hear the wolf cry. That's also another symbolism. And then we have another symbolism of death, but with the hope of life when she hears the baby cry. And the biggest symbol of rebirth is obviously when she walks out of the capsule and takes her first steps on a very, very primordial landscape as a beautiful symbol of human resilience as a species as a whole.
And frankly, if I may,
yes,
it
of
looks
course.
like the new Eve.
Exactly.
You know, like
Yes, a new
she
world.
appears
And
as, you
she
know,
does.
the new,
And,
yeah, yeah.
and I actually
yeah.
realized this today when we were rewatching. It's my 4th time I see the film. So I realized the landscape was very primordial. It almost looked like, you know, the land before time, like Jurassic Park, like all those very primal movies that we watched. And also the frog, if you saw as an amphibian, was also another symbol that I realized today when we watched. And I saw an article, I read an article a couple of days ago where a child psychologist actually talked about the development of children through the film Gravity, which I found to be extremely interesting. Of course, she went through the concept of the fetal position in the womb. And what was really interesting is when Ryan was mesmerized by the sounds that she heard, it was more of a melody and a tempo, and she couldn't really make out what they were saying or what the noise was. So she didn't really comprehend the semantics of what was said. And this is a very interesting part of child development of sound. And then we obviously see her taking her first steps like a toddler, coming out of that capsule and going into this new world. So in this development and in this progression, what we see throughout the film is a single human being that really echoes maybe the achievements of the entire species.
Yeah.
Yes.
True. So now, I'd like to do a final experiment with you, and I may need an assistant, so I don't know if you would like to come, if you want. Just for a quick thing. Now, it's about this scene that you've seen, you know, in the movie, and what I will use, so let me just that, you will see. It's very simple. So now what you have here, the system you have is a heavy ball and a small ball. Can you take it? No, you put it like this. You know, your time to say. Now, drop it. What happens? In fact, you have the small ball, and it's about, you know, transfer of momentum. So it was falling onto that, and what you see is in fact a small ball has difficulties, you know, giving energy to the other one. Okay? Now, so what it means, a small ball has difficulty transferring energy. What you have here, you've got a big space shuttle. Okay? You've got small debris. So how can you imagine that the space shuttle, even if they receive 1 million of those small particles or things, in fact, it would almost not affect the space shuttle. So this is totally wrong. Okay? So you won't have this happening because this is big mass. So it's exactly, you have a truck, you want to push the truck, I mean, you need to push hard. You know, to move the truck. Now, imagine that you have, you know, this big thing. Now, we put that on the top. You drop it. No. You take the basketball. No, from the side. As you did. Perfect. Okay. And now, give it. Okay. Yeah. You see how the particle, you know, would not the big one, it's the small one. Because those are the most dangerous in space. So, thank you very much. If you see. So, now if I move, just to show you, it's a small debris that is 1 centimeter, large, but with the speed that you have normally in space. And this is a simulation. I mean, it's the real, coating, the real coating of the ISS, and they made tests on the Earth to just simulate what would happen. And that's typically, so imagine a 1 centimeter, a small piece at the speed that you have up there. And that's the real danger. It's not what we've seen in the movie where you have thousands, going on. It's just the one, you don't know where it's coming from, and that can make a hole, And this happens. And just to show you, because this is a real problem, and this is known. Now, if I show you here, so you've got, so it's about all the debris. You've got the blue ones and the red ones. The blue ones are the ones that are big enough to be monitored. Those are the rockets, and pieces of rockets, okay? Those are also the satellites that are still there but are not functioning anymore. You can see them. And you also have 21,000 debris that have more than 10 centimeters. And as we speak, they are all monitored. So 36,000 debris, are permanently monitored. So you've got radars, you've got telescopes just looking and watching them, just to make sure that if you have a satellite, if you have a space station, if you have a spacecraft going, they want to make sure you avoid those pieces. And sometimes it slows down missions, or they just move, the trajectory of the spacecraft just to avoid them. Now the real issue is there. And the most dangerous ones are the ones that are larger than 10 or smaller. What you can see, you have almost 1 million of them. Okay. So in fact, when you go to space, there are a lot of small debris everywhere. Okay. However, if you look at the statistics, because with all the spacecraft that are in space, in fact, over 5 years time, you've got only 3% chance to get hit by one of them. Because there are not too many, I would say. You got 3% over 5 years. So if you go in space, if you stay 3 months, in fact, you've got a very small possibility to be hit by that. Okay, but still, that's a lot. Okay. But now, more frightening, because I'm telling you that there are many debris, but now, look at the evolution of the debris over the last few years, okay? So what you can see here, okay, what is more important? So this is the total. These are the small debris, so the ones that are dangerous. Those are the spacecrafts, and those are the remaining, but the big pieces. So I would say this is not dangerous. This is, in principle, not dangerous because they are big, okay? The real danger is that. You were talking about a Chinese, satellite that has been destroyed by the Chinese. Here we go. In 1 second, they increased by 30% the number of debris in space. In 1 second, they destroyed it, and they did that. The second one, that you can see, the second bump, was 2 years later. It was a Russian satellite that went into a military American satellite. So they did it on purpose, crash. And so those two, you can see where we were, that was okay, bing, bing. And now this is due to the fact that we are sending more and more and more satellites. And because you put more of them up there, you have more debris automatically. And so you can see that that's stupidity, There are treaties that are preventing that, but of course they just said, we don't care. And now, just to show you where we are heading towards, this is the number of satellites that have been launched between 2009 and 18. And between the estimate between 19 and 2030 approximately, is that will increase by 300%. So it means at the moment, you know, we are becoming crazy and sending. So we are increasing the number of debris up there, and therefore you are increasing the risk to go to space, you know. And so that's something we have to be aware, is that people have to be extremely careful, because now it's cheaper to go to space, and people don't necessarily, you know, take it seriously, you know. Now, just to mention one thing, because we are from KAUST, we have been discussing with the Saudi Commission, so there are discussions at the moment, you know, to work between KAUST and the Saudi Commission. So we brought astronauts even to discuss about the future, because we are discussing with the Saudi Space Commission to develop a new aerospace program, you know, for the future Saudi students who would like, you know, to participate into the space exploration. So it's just to tell you that the story is beginning, and I say, to conclude, be part of the story. So thank you very much. So if you still have questions, I know it's late, but feel free if you have more questions. Yep. Questions or? Yes, please.
How do they regulate their blood? Because in space you said it's in their head, so how do they keep it at a normal?
So how they do it? First, they do a lot of exercises.
Mm-hmm.
And when you start, for example, running, so in space, in fact, your blood starts re-equilibrating. So it's you can balance back by doing some exercises.
Oh.
And so they do a lot of exercises to prevent that. Because otherwise, if you don't, you know, if you just stand, in fact, this will be a problem very quickly.
Mm.
Yes? Yes? So again, say No, go ahead.
Is it possible for humans?
There are no stupid questions, there are silly answers, but
Okay.
go ahead.
Is it possible for humans outside Earth to encounter other species around them, or is it not possible?
Very good question. No. It's very simple. First of all, no, this is a very important question, and that's exactly what I was saying at the beginning, because it brings a lot of existential and philosophical questions. Now, your question, you know, is there life, first of all, is there life outside? You would have asked me before 1995, okay, I would have told you the probability is very low, okay? Because for the first time in 1995, we discovered extrasolar planets. So it means planets that are not around our sun. As we speak, okay, we have discovered more than 5,000, so proven bodies, almost like the Earth in some cases, you know, like you may have 100 that are Earth-like. There could be atmospheres, there might be water. Now, whenever you look very carefully at almost any star, okay, most frequently you find planets, okay? Now, when you watch at night the sky, that's our galaxy, that's about 10 million of billion of stars. That's our galaxy, okay? But there are more galaxies than there are stars in our galaxy. So it tells you that there are billions of planets everywhere, okay? So when you are asking me, is there a chance? I would say yes. Now, the other side of the question is, can we communicate? Will we be able to communicate? I doubt, or even to see them, for many reasons. First of all, it's very far away, okay, number one. And when you look at the history of the universe, we might be, you know, plus or minus a few million years. But we are among the first generation of potential life as we know it. And the last point I would like to make on that point, because it's an interesting one, the last point is the fact that we have to be careful about what we expect or project on this type of life. Just to give you two things. The first thing, when you look at our sun, okay, what is the color of the sun from your eyes? You know, yellow, typically. That's what we call yellow, but it's white, but it's yellow, okay? Now, if you look at the rainbow, okay, what is the central color of the rainbow? Yellow, yellow. So it means our eye has adapted to the maximum of light of the nearest star. That is, okay. And as you know, there are animals who see infrared. There are some others who look at use UV to see things. So imagine that now we would not be close to the sun, but close to a red star or a blue star, we would see differently. So even simply our eyes would be different. Now, even your body, if you go on the moon, you would weigh 6 times less. You would go on Jupiter, you would weigh 30 times more. You would go on the sun, if you could, it's 1,000 times heavier. Okay, so depending where you live, you may not be able to be, let's say, 1 meter high or 2 meters. You might be, that small. So you may be just watching a blue star with whatever. And so what we project, about aliens, we should be extremely careful about what we call aliens. There might be just fungi, or there might be not even plants, because plants need oxygen. So what you have to keep in mind is there is a great chance that in the entire universe, there might be many types of life, let's say, but because of the distance and the type, it might be very difficult to interact with them. Okay, it's a long answer, but...
Lama, yes, maybe
Can I quickly add,
please.
very, very, very quickly, because a subject that I'm passionate about as well. Just look at messages that have been already sent in terms of trying to contact extraterrestrial beings. It's been done, like Arecibo in the 70s, and then other spacecraft that has gone up with certain symbolisms, like the Pioneer plaque, like Voyager. So we've tried as species. Was it the right way of communications? I mean, it's up for debate. But as species, we've tried, and it's our way of leaving our mark, really. It's not about communicating, but in a way, it's always us looking back saying, we're here, and we matter as a species. That's really always what we kind of want to convey to any extraterrestrial or any other sentient being that we find that we, want, I mean. And then you have other debates, because there's always two sides to every story, like Stephen Hawking, who said, don't send these messages because they could be hostile. We don't know who's going to find them.
You never.
So it's a huge debate, but it's definitely one that if you look into, you'll find that there has been attempts that already happened. And then again, the media and film and Hollywood have given us this persona of this alien, with this little silver man with the big eyes, but then it can be the single cell organisms as well. So it's a huge debate.
And if I may, now be even more philosophical, if not political.
Yes.
We have been starting to fly, less than 150 years ago, even less. So imagine, maybe we can do a lot, but something that is more problematic, as you know, what have we done in those 150 years in terms of pollution? Aren't we destroying the little planet we are working on? And I think before even being concerned about what's going on out there, let's make sure that we survive long enough to maybe even communicate. I would say.
Yeah. Going back to gravity, I think it's one of the also how we said how precious life is, and we're in a margin, how precious Earth is. We're in a margin between sky and ocean. And it's a very narrow margin that's very clear in the film, especially at the end when she, is back in a state where she can't breathe and she needs to come out. So you realize how there's a very precious, feeble line of this very narrow margin between sky and water that we need to, take care of.
And remember, even when we are in a plane, we go up to 10,000, so 10 kilometers. Think about the size of the Earth, 6,000 kilometers. So we are living on a thin layer, but really thin, like paper, large compared to, let's say, a mountain. We are just on this tip, and we are clever enough to destroy it, to this very, balanced equilibrium where life could appear. And so for me, if there is one thing exactly what they were saying, those astronauts, is you discover how fragile we are, how small we are. And I think for me, what is more important, let's make sure we keep it, It's, any final, yes, maybe, because I think it might be late. But it's
very basic. I just wanted to know why you said that we know we're one of the first species of
Sorry?
that
No?
kind. I think you said earlier that we know we're one of the first species of our kind.
Yeah.
Did I understand you correctly?
Yeah.
I was just curious to know why, or
Why?
how we know
Okay.
that.
It's very simple. Okay, what are we made of? Mainly carbon, oxygen, and hydrogen, okay?
Stuff.
Yeah, so those are okay, that's chemistry, but you know it, carbon, oxygen. Now, if you look at the universe, 98% of the universe is made of hydrogen. So carbon and oxygen is rare, really rare. So how do you form oxygen and carbon? In fact, the only way to do it is at the very end life of a star. So when you look at a star, typically a star will live, if you take the sun, 10 billion years. Okay, and we are at the moment at 5, for the sun. But there are some bigger stars that don't live that long, maybe 1 billion years, and some even hundreds of millions of years. But now, to create oxygen and carbon, you need a star to live, so let's say 500 million years, okay, and explode and give it back to the space. And then within this, you create a new star. And you need to enrich it enough, okay, so that you have enough carbon and oxygen to bring the bricks, the elements to make life. And when you look at the history of the universe, we might be, if you look at even the sun was created 4.6 billion years ago, with the Earth, and that was only 7 years after the beginning of the universe, as we believe it, okay? And therefore, in this story, you didn't have a lot of lives of stars, okay? And you need the minimum of them to concentrate enough the carbon and the oxygen. And so, you may have enough carbons and oxygen elsewhere, but you could not say that it has been billions of years since there were enough carbon and oxygen. So in fact, we are, I would say, among the first generations, but I'm talking about millions of years, okay? But for the last maybe 10 millions of years or hundreds of millions of years, the first generations that can have life. So it may not be that frequent, but it could be everywhere. Got it?
I think it's a beautiful thing to end with, that we are made of star stuff.
Yep.
We are made of the stars.
We are stardust.
We are stardust, exactly.
Yeah,
so
yeah.
it's a beautiful thought to conclude with.
And this would be another nice
Yes.
talk if we
For our next
about
talk.
the life,
Yes.
life of stars. So, thank you very much again.